let's consider the entry in the L1 place of the linear combination of these rows. Okay, our linear combination is C1R1 plus C2R2 blah 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 plus CMRM. Okay, now if we consider the L1 entry of that result, since we're saying that the linear combination is 0, this L1 entry must also be 0. Okay, so we have 0 equals C1R1 L1 plus blah blah blah, like this. Okay. However, the matrix is in echelon form, so I could continue this. This has the stair-step form. Okay. So if I take a combination, for instance, if I took C1 times this one, plus C2 times this one, and if I added these up, okay, then what would I get here? I'd have C1 times this entry. I'll just write it as star. Okay. And as long as this entry is not 0, then this entry would not be 0. Okay. Or you could say that the result says that if this is 0, then C1 must be 0. Okay. So that shows that we cannot have R1 in this linear combination. So that proves my base case. Okay. The inductive step is pretty much the same as the base step. Again, consider equation star. Let's go back and see that. Equation star was this one here. Linear combination of rows is equal to 0. We will prove that if coefficient Ci is 0 for each row index from 1 to k, then Ck plus 1 is also 0. Okay. We focus on the entries from column Lk plus 1. Okay. So I'll just draw the picture again. We have our echelon matrix. We have our stair-step form. And suppose I'm considering a combination of rows starting from this row, this row here. Okay. Again, of all these subsequent rows, only this row has a non-zero entry in this column. So there's no way that I can take a linear combination of these rows and get a 0 entry in this column unless the coefficient of this row is 0. Okay, so that establishes the induction, which establishes my final result. Okay, so here let's show a particular example. In this non-echelon form matrix, the third row is the sum of the first and second. You can verify that. But after Gauss's method, there's no way to make the sum of these two rows be equal to 0, because as I mentioned, if your linear combination includes this row and has non-zero coefficient, then the first entry in your result will also be non-zero. All right. So now we have enough to show the result that we want to show, which is that each matrix is row equivalent to a unique reduced echelon form matrix. Okay. Okay, here's the proof. So fix a number of rows m. We will proceed by induction on a number of columns n. Okay, so if you think about your matrix here, all right, we know that we can have m rows and n columns. So first let's consider a matrix with one column. Okay. Now if we have one column, what are the possible echelon forms? Well, if the original matrix is 0, then the echelon form is 0. But if I have a one column matrix where any entry is non-zero, suppose this entry is non-zero. Okay. Now I don't care about the other rows. I can take this entry up to the top by exchanging rows. And then by row operations, I would get all the other entries 0. And when I do reduced row operations, I would make that first entry 1. So the only possible reduced echelon form is 1 and all zeros here. Okay. So what does that show me? That shows me if my matrix has one column, there's only one reduced echelon form matrix equivalent to it. Either the reduced form echelon matrix is 0, in which case the original matrix was 0, or if the original matrix is not 0, it reduces to this form. Okay, so we have established the base case when the matrix has only one column. Okay. Now let's assume the case where n is bigger than 1, and that all m row matrices having fewer than n columns have a unique reduced echelon form. Okay, so let's take this, we're now taking a more general matrix here. Okay, and this is M, and this is N. Okay. Now what we're going to do is split off the last column. Okay. Now if we consider this matrix here, which he calls A twiddle, I think, this matrix only has n minus 1 columns. Right? And when we reduce this matrix, there is a unique reduced row echelon form that's established by the inductive step. Then all we have to do is show that the last column is unique as well. So we'll see how that works out. Okay. So as I said, let A hat be the matrix consisting of the first n minus 1 columns. Any sequence of row operations that brings A to reduced echelon form will also bring A hat to reduced echelon form. Okay, because A hat is just going along for the ride. If you look at all the examples that we've done, that's always true. A hat will inherit the reduced echelon form from A. But by the inductive hypothesis, this reduced echelon form for A hat is unique. So if the two reduced echelon forms B and C differ, then the difference must occur in the last column. Okay, so we've focused in on the case just to see if the last columns are equal or not. Okay, so our original matrix A can be associated with this system of homogeneous equations. Okay, if there are two reduced row echelon forms for A, both the matrices correspond to systems that have the same solutions as the original solution. Okay, so the solutions of this system must be equal to the solutions of this system, which must be equal to the solutions of this system. Now remember, we've shown that all these coefficients here, up to the very last ones, up to the coefficients of xn, are equal to the corresponding coefficients here, up to the very last coefficients in each equation here. So all we need to do is show that these coefficients here are equal to these coefficients here. Okay, so B and C differ only in column n. We've shown that they differ at most in column n. And suppose they differ in row I. Well, they have to differ in some row, so suppose they differ in row I. So subtract row I of triple star from row I of double star. So subtract row I of this system with C's from row I of this system with B's. And we know that the coefficients to the left of this line are all 0. So here we're going to get 0. And if you work it out, you'll see that what's left is only BIN minus CIN times XN. Now we're assuming that these are different, and we're going to show a contradiction from that. So let's see. So that gives us this equation. Since these are not equal, that gives us xn is equal to 0. Okay. What does that mean? Xn must have a specific value. Therefore, xn is not free. Okay, since xn is not free, that means the nth column must contain a leading entry, because we've seen that any matrix and any column without a leading entry gives us a free variable. Okay. So so we can show that there is a leading entry in the nth column. But that's a contradiction, because B and C are equal on the first n-1 columns. A leading entry in the nth column would have to be in the same row. And with both matrices in reduced echelon form, both leading entries would have to be 1. Okay, so what's he saying here? Let's look at B and C. Okay. Again, we've got this line here. This is B. And this is C. We've got the dotted line. Oh, side color line. Let's do it here. Now remember, all the entries to the left in B are equal to the entries to the left in C. Now we already have B in reduced echelon form, so we have this stair-step form. Okay. And we must have the very same stair steps in C, because these two matrices agree. So I'm going to try to eyeball it. So we're going to have the very same stair steps. Okay. Okay. Now, what row has the next leading entry? Well, it has to be the next row here. It's the row with lowest index that has all zeros. Right? So the leading entry in this last column must be this row that has all zeros. Similarly, the leading entry in B must be in this row that has all zeros. Okay? So in fact, it's the very same row, because what we have here, this stair step, is the same as this stair step. So that tells me that the leading entry in matrix B in column N is the same as the leading entry in matrix C in column N. The leading entry is in the same row. But what do I know about reduced echelon form? I know that the leading entry is always 1. So what have I shown? I've shown that this entry of B must be equal to this entry of C. But up here I've assumed that they're not equal. That gives me a contradiction. Okay? So what am I contradicting? I contradict my supposition. Whenever you have a proof by contradiction and you come up with a contradiction, look at what you've supposed. And what you've supposed must not be true. So here's what I've supposed. I suppose that they differ in row I. Right? So since I've derived a contradiction, this supposition must be false. B and C cannot differ in row I. If they don't differ in row I, they don't differ in any possible row. They must be the same in column N. Okay? So that means, in fact, the column N of B is equal to column N of C. The two matrices are, in fact, equal for all columns. Okay. These inductive proofs take some getting used to. I advise you to read the book again, watch the video again. It's a standard mathematical argument, and as I said, you just need to get used to it. Okay. So our result is that the reduced echelon form is what you call a canonical form for row equivalence. Okay. What that means is that the reduced echelon form matrices are representatives of the classes. As I mentioned before, each one of these equivalence classes, row equivalence classes of matrices, has exactly one reduced echelon form that's associated with it. Okay. So if I want to decide whether two matrices are row equivalent, well, then they must be equivalent to the same reduced echelon form, right? Because if they're in the same class, they're in the same class with exactly one reduced echelon form. So I can reduce each one separately to the same reduced echelon form. Okay. All right, so when you reduce the first one, you get this echelon form, reduced echelon form. When you reduce the second, you get this reduced echelon form. This follows that the original matrices cannot be row equivalent. Okay, that's it.